Electricity today appears simple at the point of use. A switch is flipped, a device turns on. Energy flows from somewhere beyond the walls of the building. Yet the path behind that moment is long and complex. Electricity used in homes typically originates far from where it is consumed. Power plants convert fuel or heat into motion into electricity, and that electricity travels through layers of infrastructure before reaching a residential outlet. Generation facilities, transmission lines, substations, transformers, distribution networks, each step exists to move energy from centralized locations toward millions of individual buildings. This structure has defined modern energy systems for more than a century. But the underlying mechanical principles that make electrical generation possible are much older. Long before large electrical grids existed, engineers were already experimenting with methods for converting heat into mechanical motion. Some of those early ideas quietly continued to influence modern energy research. Throughout industrial history, most large-scale power systems have relied on similar mechanical foundations. Steam turbines, internal combustion engines, and gas turbines all follow a familiar pattern. Heat energy creates pressure. Pressure produces motion. Motion drives a generator. These systems became dominant because they scale efficiently. Large facilities can produce massive amounts of power and distribute it across wide regions. Over time, improvements focused primarily on increasing efficiency, expanding infrastructure, and stabilizing distribution networks. For households, interaction with the system remained relatively simple. Electricity was purchased, measured by a meter, and delivered through a centralized grid. Within that structure, the mechanical processes responsible for generation remained largely invisible to the end user. Despite decades of technological advancement, the centralized model introduces certain structural characteristics. Energy must travel long distances between production and consumption. Infrastructure must be continuously maintained. Large generating facilities require significant resources, planning, and regulatory oversight.
For this reason, most mechanical energy systems have historically been designed for large industrial scales rather than individual use. When similar systems are reduced in size, efficiency often declines. Thermal losses increase. Mechanical tolerances become more difficult to maintain, and energy output becomes more limited. As a result, small-scale power generation has historically been less common within residential environments. This structural imbalance between large-scale production and small-scale consumption has shaped the architecture of modern electricity systems. However, not all heat-driven mechanical systems were originally designed with large power plants in mind. In the early 19th century, engineers explored several alternative approaches to converting heat into motion. One of the most notable appeared in 1816 when a Scottish engineer named Robert Stirling introduced a new type of heat engine. Unlike steam engines that relied on high-pressure boilers, this design operated through a closed cycle of gas expanding and contracting as it moved between hot and cold regions of the machine. The concept was mechanically simple but thermodynamically distinct. Instead of explosive combustion or steam pressure, the engine relied on controlled temperature differences to create motion. Over time, variations of this concept appeared in research laboratories, experimental vehicles, and specialized engineering projects. The basic idea continued to surface in different forms across more than 2 centuries of mechanical experimentation. In recent years, some educational materials and technical guides have revisited historical engine designs like this one. These materials typically examine the mechanical structure of the system, the thermodynamic cycle involved, and the historical role the concept played in early energy research. Some guides also document how simplified versions of such engines can be assembled for demonstration or experimental purposes, often using modern components that were not available during the original invention. These documents generally focus on explaining the mechanical principles behind the engine, rather than positioning it as a replacement for existing power systems. In most cases, they present the concept as an example of how historical engineering ideas continue to appear in modern discussions about energy conversion. 2 centuries after its introduction, the underlying concept remains a small but persistent part of engineering history. While large-scale electricity production continues to rely primarily on centralized infrastructure, the mechanical principles behind energy generation still trace back to a series of early experiments in heat, motion, and pressure. Some of those experiments became dominant technologies. Others remained quieter ideas that resurfaced periodically in research, prototypes, and technical discussions. Understanding these historical mechanisms does not necessarily change how electricity is used today, but it does illustrate how many modern systems originate from engineering concepts that were first explored long before the electrical grid itself existed.